Okay, start recording. And hello, everyone. I'm very pleased today to introduce Dr. Xuemei Zhai, who is a postdoctoral scientist um, at the National Center for Coastal Ocean Science. And she has taken her PhD. He has gotten her PhD at Harvard University in 2021, working on marine biology. Before that, she taught at Harvard University for several years, evolutionary biology and global change. And she will be talking to us about diel migration and how important it is in the carbon budgets in the ocean. Xuemei, we are very happy to have you today. Hello.
Thank you so much, Natasha. Hello, everybody.
Hi.
Hello.
So I will share my green screen and share my. Okay. Sorry.
Okay.
Can you see me now?
Use present mode. Yes, great. Thank you.
Okay. Thank you so much, Natasha, for give me the chance to share with everybody my work with Professor Glenn Flower of MIT. This work is mainly my work of dissertation, which was completed 2021. And even though the subject is what makes Stellwagen Bank a productive coastal region, in this talk, I will show mainly the impact of zooplankton diel migration and its ecological consequence in this region. We choose Stellwagen Bank as a case study. I mean, this is a very small area. In this talk, we are going to emphasize zooplankton diel migration and a biological pump. So biological pump is a term which was proposed last century, and it is a main study subject by some important international projects, including GISS and also including exports. This is a figure presented by GISS, basically show the flux of organic matter from surface to depth, the biological pump. And I'm sorry, the phytoplankton, zooplankton are not very clear, but they're almost top, right below the surface. And so phytoplankton absorb or uptake carbon through photosynthesis in the water, and also through the grazing process, zooplankton absorb the carbon, and both of them also via their excretion or mortality, they form some detritus or POC, and they become a bigger particle, and this particle has a higher sinking rate, so they can sink through the stratification layer to the deeper ocean. On the other hand, zooplankton has a very important behavior, which is diel migration. They move to the surface water after dark, where their food phytoplankton is. After feeding all night before dawn, they're going to sink to the bottom where there's no light. There are several theories about why they do the migration, and the dominant one is basically predator avoidance, which they can escape being preyed by their predators. it's just like in the biological world, everything is about to eat, not to be eaten. So this migration physically can bring much bigger article with, basically with the carbon to the much deeper water. The migration depth could range between tens of meters to even hundreds of meters in deep ocean. So these are some of the species which participate this kind of movement. And some people believe this style migration is the biggest biological biomass movement through night on the Earth. And in this study, we can tell from the work in 2019 and 2013, they show how this is the field work. They show the movement of zooplankton overnight. Depth could from several tens of meters, could from 10 meters to like 90, 80 meter change of water depth. And besides the biological pump, my advisor in Harvard, Professor McCarthy, also proposed a term of whale pump. The reason I mentioned the whale pump because in the region where I'm studying is basically a whale feeding ground. So the whale is much larger animals. They can, we all know when a whale died, the body, they carry huge amount of carbon sink to the bottom, and also their feces. So the whale feed in the surface, but their feces will sink to the bottom. So this is another so-called whale pump. Have the similar function of a biological pump. You can separate them or you can put them together. They are all biological. So I will briefly introduce the region where my study is focused on. It's Stellwagen Bank. This is a very small area. It is a national marine sanctuary. Basically, it's set in order to protect whales. Particularly, there's an endangered species, North Atlantic right whale, which they feed. This is their very important feeding ground. The right whale, there are about 20 to 200 to 300 individuals of right whale now. So their existing number is even fewer than panda. So they are very much needs to be protected. So the setting of National Marine Sanctuary is mainly to protect right whale and humpback whales, which are feeding on Stellwagen Bank and its necessity. The water depth over this bank is pretty shallow. It's just over the bank is between 20 to 40 meters. Surrounding the bank, the deepest part is on the west side, which is about 100 meters. So you can tell each spot is where you can see the whales. So this just to show in order to avoid the high number of collision between commercial ship and whales, the Massachusetts government has to make a law to change the route of a commercial ship, even though it will cost them a little bit more time, is just to protect the whales. So what do we know about the underwater banks and mount? So there's some series of study. Typically, in this region, in the highland of like in Pacific, or particularly in Pacific, there are some underwater banks or mountain. And along the coast, there are also some the biggest one nearby us is Georges Bank. I choose a much smaller one to study. So there's a high production and biomass near this region, and they have a pretty strong horizontal sea currents, and also they have unique seafloor features. And the zooplankton diel migration show particularly ecological impacts in this region. So these also have strong vertical nutrient fluxes, including upwelling and downwelling. So this is the topography setting of Stellwagen Bank. The top figure is more realistic, which is modified from Lea et al. 2010. And the bottom one is our model setting in this study. We choose the middle of the bank has 0, and to the left, to the right, each has 60 kilometer. And the water depth, total water depth is 120, and right above the bank is 32 meter. So the physical condition of this region is this has a pretty strong tidal current, and also has a Gulf of Maine coastal current in this region. So you see so this bank is between Gulf of Maine and Massachusetts Bay. It serves as a boundary of Massachusetts Bay. So the biological conditions of this region is it has very high production, and also has high diversity, both benthic and pelagic. So historically, this is an important commercial fishing ground, but the fishing activity is banned because this now is a sanctuary. And this is also a very important whale feeding ground. So just think about one whale can consume up to like 2,000 pounds of plankton or small fish per day. So obviously there's a lot of food in this region, in this small region. That's one of the reasons trigger us to study why there are so many whales feeding here, and which means there's a high biomass here. So now I'm going to introduce the method and model which we used in our study. And the model is designed of 5 biological state variables: ammonia, nitrate, phytoplankton, zooplankton, and detritus. Okay. Sorry. So there is 2 species of nitrogen. And this is the formula, the functions we used in our 2D model for the 5 state variables. These include advection by currents, diffusion, uptake, and grazing, and also, of course, mortality. These 5 equations are modified from Dr. Patricia's work in her 2007 dissertation. We add a special term here, which is WZ in second function, vertical migration, which is add to the Z part. So the 2D model is based on tidal equations. So this is the equations. And this is the tidal flow streamlines based on our equations, which is not. So the processes have been addressed. It's number 1 is zooplankton diel migration. Number 2 is tidal currents. And also we have addressed, in my dissertation study, we have addressed all this, but due to the limit of time, I'm not going to present today. It includes topography, water depth, and diffusivity. So this is the light we used. So the 1D model we use, this is the WZ, which is, we call it migration rate. it's not the depth which the zooplankton reach. It's the total their that's the total migrating pattern and the distance. So it's not the distance. It's not the vertical distance of their migration. So this is the migration pattern based on this equation we got. Uh, this is the 1D model result based on our model, which this is the daily average of biomass, including phytoplankton, zooplankton, and detritus nitrate in the water column under the condition of different zooplankton diel migration rates. So I choose 7. So all these effects is without predator avoidance. I later edited the study. I add the predator avoidance. So from the without predator avoidance, we can tell that the vertical migration for zooplankton is basically negative effect on their biomass. So without migration,
Xiaomei,
yes,
sorry to interrupt you. Can you repeat in this figure what the different colors are? I can see very clearly the
okay.
dots.
So the blue line, uh, is the migration. There's no migration, and
Mm-hmm.
the purple line is with the longest migration. So
Okay,
the
I
blue
see.
line is 0, purple is 120. Between of them, I have every step is 20.
Mm-hmm.
So if we only see the blue line now, that
Yes.
zooplankton has the highest biomass without migration, and the nitrate has the highest amount in the deep water. I mean, below the surface. I mean, in the top 10 meter, they all almost to 0.
Mm-hmm.
And for the detritus, its behavior is very similar to the zooplankton, but when the migration rate is higher, it's more affected by the phytoplankton. And for the phytoplankton, its highest biomass shown in the strongest migration, which is understandable because the migration of the zooplankton means they leave the region or the water level where their food is. So this reduce their feeding or their grazing time. So their grazing amount reduced significantly. So this
Okay,
is without considering the benefit of predator avoidance. So
I
if we
see.
don't consider the predator avoidance in the 1D model, we see only negative impact on zooplankton.
Mhm.
But I also, in my later result, I consider the predator avoidance, but it's pretty primary. I need to do more tests, including to calibrate the predator force on the zooplankton. So this is the in 15 days we can see this is a phytoplankton and zooplankton. Their biomass through the water column uh, in 2 different conditions. One is WZ, the migration rate is 0. The bottom panel is the migration is 120. So when without migration, the phytoplankton biomass is um, fairly low, but it has. I mean, soon I will show you the photosynthesis. Their primary production is not low, So the zooplankton biomass is high in the top 10 meters because there's no migration. They have, food available. So they are enjoying their life without considering predator. So there's no predator force here. And with migration, and we can tell this pattern, the right bottom is the zooplankton with migration. It's a 24-hour cycle. You see, when in the night they surface, and when during the daytime they hide in the bottom. So with the migration, the phytoplankton grazing pressure is reduced. So the phytoplankton biomass increases compared with no migration. So this is the result of detritus and nitrate. So with no migration, the detritus in the top 10 meter is high, corresponding to the high biomass of zooplankton. And with migration, it's in the surface, it's low. I mean, the total detritus is low, corresponding to the low biomass of zooplankton. The nitrate, on the other hand, is with no migration, the nitrate amount concentration is high, below 30 meters. And with migration, nitrate has been consumed. Even the bottom one has been reduced.
So, what consumes nutrients, nitrate, for example, at 100 meters and 150 meters depth? Why is it so reduced? Do you have some kind of remineralization in the model, or why is it reduced compared to the no diel migration?
Integral of biomass of phytoplankton and zooplankton through the whole water column. So this is the value based on the test of no migration to 120, which is the highest migration. So with no predator effect, the zooplankton biomass is much lower. But if we consider the benefit of avoiding predator, a 120 migration rate compared with no predator. The reason I said I need to do a more aggressive test of predator pressure is in reality, the zooplankton performing migration is basically ecologically it's beneficial to them. So they spend the energy to migrate and to stay almost half of their time not feeding. But they reduce the danger, the risk of being eaten by their predators. So this is the vertical integrated uptake of nitrate and ammonia by phytoplankton and total grazing amount of phytoplankton by zooplankton through the water column for different zooplankton migration rate. So the grazing amount is low because they don't have enough time. The grazing period is shorter with a deeper migration. And the uptake of ammonia, on the other hand, has an interesting uptake increase after 100 meter. This is caused the higher concentration of ammonia and also the higher biomass of phytoplankton. So the summary for the model, for the 1D model, the effect of migration is to the phytoplankton is positive. They increased their biomass by 126%. For the zooplankton biomass, without considering the benefit of avoiding predator, is purely negative. They reduced their biomass by 98%. And the photosynthesis rate, interestingly, is also lower with migration. And the zooplankton grazing, understandably, is also 98% lower. This
Oh,
eventually reflects on the biomass. Yeah.
yeah, Xiaomei,
Yeah.
can I ask you? I understand that you prescribe the same rate of grazing for the zooplankton when it is at the surface feeding at night, or in the no migration model. Is the same again, right? So in both cases, the rate of grazing is the same. Whereas, for example, one could assume that if they are at the surface all day long, they graze not as efficiently. But when, for example, they migrate only at night and they're near the surface, they are actually grazing much faster. They're more efficient in the uptake. So the overall effect could actually be no change in the phytoplankton biomass. Is that correct?
That's
Do we have
possible.
observations
The
that
grazing rate, I have the maximum grazing rate is the same, but the actual grazing rate is controlled by the concentration of phytoplankton biomass.
right, right?
Yeah. Mm-hmm.
So for half of the day, the phytoplankton grows uninhibited because there's no zooplankton to take it up, and then for
Yes.
the rest of the day, the phytoplankton gets a term, has the same efficiency, the same loss essentially. So I see. So it does make sense, for example, why phytoplankton eventually would increase, and then why the zooplankton biomass would decrease because they actually feed less in
Yes.
the migration model. Now,
Yes.
but in why I don't understand why photosynthesis though is reduced if you have a 126% increase in phytoplankton biomass. Why is the photosynthesis decrease?
So in the biology, there's so they have comparably with the grazing of zooplankton is actually beneficial for the phytoplankton because the availability of nutrients to the unit of phytoplankton is higher.
I see. I see.
Yeah.
So it's because there's more
The,
nutrients available, and that
yes, the
reduces
nutrients
the.
availability is not the same.
Yeah. Okay, go on.
Okay. All right, let's go to the 2D model. I hope I have, okay, I will hurry up. So in this 2D model, we study the effects again, the effects of zooplankton migration. And the other important process is tidal currents. So we compared with and without tidal currents. The tidal currents we choose is 10 kilometer per day, which is 12 centimeter per second. This is a typical tidal current speed far from the bank in this region. I also did the bank width comparison, but I'm not going to present here today. So this is the effect of zooplankton diel migration and tide on phytoplankton. This is the pattern of upper 30 meter, which is right up the water depth right above the bank. So the left panel is phytoplankton, and with the left panel is without phytoplankton, without tidal currents. The right panel is with tidal currents. The top panel is without migration. The bottom panel is with migration. So on the top left,
What is the horizontal axis again? Distance from the bank center? Okay.
yes, the distance from the bank center, I only show minus 30 to positive 30 kilometer.
Okay.
So without migration, without tides, it's basically pretty the same through the whole domain. This is the 60 days. I will see why I need 60 days. It's because the tidal period in this region is approximately 15 days. So I use 60 days. It's each tidal cycle is 12 hours, some point something, not exactly 12 hours. Anyway, so uh, on the top with tidal currents without migration, there's some, you see the pattern. It's basically the line is a daily cycle, but you
Yeah.
already can tell from the top right the tidal cycle. You see there's briefly 4 tidal cycles.
Yes.
At the bottom, without tide, with migration, interestingly, the on the in the middle of the bank, the biomass of phytoplankton is very low. With tides, with migration, the biomass of phytoplankton is centered along the bank. And this is the
And
similar.
why is the frequency? And why is the frequency so much? So now the frequency is in between the daily and the tidal, correct?
Yes.
Why?
So the daily cycle of phytoplankton is showing the change of light. And the tidal cycle shows the effect of tides on this system.
So the multiplication of the two is giving you that higher. It seems to be, I don't know, 2 day cycle. Seems to me, I don't know. I can see very clearly.
Uh, no, it's if you see the top right, it's
The bottom, I'm
basically
looking at the
see
bottom right.
four. Oh, the bottom one, the bottom right. It's
Yes.
also roughly a kind of. It's not very clear, but roughly a 4 cycles.
Okay, let's go on. Yeah, we can
You see,
discuss that more
yeah,
later.
yes, okay. So this is the effect on the zooplankton, also in the pattern of upper 30 meter. I put again on the left panel is no tides, right panel with tides. The top panel is with no migration, bottom panel with migration. So with no migration, only tides, that already show some impact on the biomass of zooplankton. And with migration and with sorry, that I have to point it out, the scale of these figures are not the same, because I try to use the same figure, but same scale, but it shows a little bit, the difference is not clear. So in order to show the difference, I use a different scale. The bottom right, the scale, the orange color is already 10. And on the bottom left, it is 2. So it doesn't mean the left has much more biomass than the bottom right. It just means I use a different scale in order to show the pattern. So for the bottom left, right, I have both migration and tides. This showed very clear the 4 tidal cycles.
Yeah.
And here I'm going to play the movie. Oh, where? Cannot find my. Sorry, I cannot find my map. Oh, okay, here. All right.
Mm.
So this show you the movement of zooplankton in the daily cycle. I have total 3 days.
Mhm.
So they come up in the night, and yeah. So sorry, my okay.
Mhm.
This is the comparison of the results again for the upper 30-meter integral of the 4 biological variables across the bank. So again, I compare. So the blue line is no migration, no tide. And the red line is no migration with tides. The yellow line is with migration, no tides. Purple line is with migration, with tides. This is showing you the total biomass of the upper 30-meter with the effect of migration and tides. So for the phytoplankton, when there's no migration, no tides, its biomass is the lowest, which is the bottom. And the tides actually increase the biomass of phytoplankton around the bank, particularly on the shoulder of the bank. It's because of the upwelling caused by the currents across the bank. And when there is no migration, but when there's no tide, but with migration, the biomass over the bank is smaller, but the biomass in the rest of the region is high. With migration, with tides, the highest biomass occurred on the shoulder of the bank. For the zooplankton, is somehow it's just the opposite. We have already seen in the previous figures show that with the migration, without considering the benefit of predator avoidance, the migration did just to make the biomass lower for zooplankton. And these tidal currents increase the biomass over the bank, particularly on the shoulder with the migration. The reason again is also because there is higher food availability there, so their feeding efficiency is higher. So the bottom two is the nitrate and ammonia. Sorry, I don't have it. Okay. The detritus is similar to the zooplankton. Sorry, I don't have enough space to put the detritus there. But this is the two species of nitrate and ammonia.
Mhm. Yes.
And this show the rate of biological processes, including uptake of ammonia, uptake of nitrate, and grazing activity by zooplankton. Actually, I made a typo. In the middle, it should be 40. The middle is not 0.
Mhm. The middle
Oh,
column,
no,
that
no, no, no,
column.
no.
Yeah.
No, I was right. No, I didn't make a mistake. Sorry, I was confused. So when no migration, no tide, this is the left panel. No migration with tide, this is the middle panel. With migration, with tide, this is the right panel.
Mhm.
So for the uptake of ammonia, so this might answer your question, Natasa. which is the photosynthesis is higher
Yeah.
because the uptake of ammonia is higher here.
Right.
And for the middle, which is the uptake of nitrate, again, it is higher when there's no migration, no tides. For the grazing rate, understandably, that the grazing when there's no migration is and no tide, it's high. But when there is no migration with tides, the grazing rate is peaked. The grazing rate peaks around the bank. And with migration, the grazing rate decreased pretty clearly. I'm using the same scale in this case.
Yes.
So for the summary of a 2D model, this result, I haven't considered the impact of predator for zooplankton. So the phytoplankton, it different from the location. For the bank center, the migration for the phytoplankton increased by 80%, but far away from the bank, it increased by 300%. For zooplankton, along the bank center, it decreased by 75%. Far away from the bank, it decreased by 90%. So the effect of migration when there's no tide. So when there's no migration, this is the difference, the effect of tides on the phytoplankton, zooplankton in different locations. For phytoplankton, the tides in the bank center, the tide effect is positive 60%, but far away from the bank doesn't affect. Again, the reason it has a positive effect is because of the upwelling. And for the zooplankton, it has a positive effect over the bank shoulder, which is 40% more. It's basically because the food is more there. And so this is my conclusion. So through this study, my main study is based on no predator avoidance benefit. So if there's no predator benefit, the vertical diel migration is negative impact, pure negative on zooplankton biomass, which is caused by the grazing rate is significantly shorter. So the phytoplankton biomass increased through the whole domain. And for the zooplankton, it increases if there's it decreases no matter with or without the predator benefit in my test. But with the predator benefit, the decrease of biomass zooplankton is smaller. And if we think about the 2D across the bank, the zooplankton biomass on the bank shoulder is much higher than the rest of the region. And the tidal currents also can impact both phytoplankton and zooplankton. It has both positive effect on both phytoplankton and zooplankton along the bank, particularly the bank shoulder. It increased by 40%. The zooplankton biomass increased by 40%, but not much change elsewhere. So based on this study, we can tell that the two of the main reasons why there is a much higher biomass over the bank is number one, there's a strong tidal current across the bank. Number two, zooplankton diel migration form a biological effect make the biomass of zooplankton over the bank, particularly the bank shoulder, is much higher. and the study needs to go further. I plan to do more tests for the predator avoidance for this study, and possibly it will be great if it can be put in a 3-dimension model and in a much bigger scale to test the biological, the zooplankton diel migration and biological pump in a much open region and a bigger scale to see their function in the carbon cycle globally. Thank you very much.
Yes, thank you, Xuemei.
I hope I didn't go over the time.
No,
Oh,
no, you
okay.
didn't.
Okay.
So, are there any questions from the group? I have a question for you.
Okay.
So this seems to have an important impact in both of the biomass, but presumably also the carbon export from
Yes.
the euphotic zone into depths. Um, Definitely near that region, in that region that you looked at, which is very influenced by the fact that it is very shallow area, and also it has very strong tidal currents. So what about other regions of the open ocean? What would you expect, or what does the bibliography suggest we should expect for the effect of diel migration in the global carbon cycle?
Number
Open
one,
ocean.
yes. Thank you, Natasha. Great question. Number one, the migration distance will be much bigger in the open ocean. Typically, could be several hundred meters. At least it will be over 100 meter, definitely across the stratification layer. And they will bring significantly the amount of carbon to the deep water. And also not only the dine in the surface water and the excrete in the deep water. It's basically like a physical carrier of carbon from surface cross the stratification layer to the bottom water, to the deep water. And that's one. Number two, um, in this in the coastal area, it's very much affected by the topography. For example, the zooplankton cannot go deeper than 30 meter because the bank itself they get stuck. In the open water, there's no such stuck area. Uh, Maybe there's some in the like in Pacific Ocean. There's here and there sporadic of a sea mountain, but it's not a main thing. So we cannot think about the zooplankton will stuck anywhere, but they will go as further as they can, so to avoid being preyed by their predator. So in the open ocean, we will think number one, the migration depth will be much bigger. Number two, the effect of a predator avoidance will be much more significant because if they're in the surface, they definitely will be consumed because the food in the open ocean is scarce. So if they stay in the surface, they will become food. If they go down, that they can largely avoid it being fed on. So that's the two part we should consider. And the number two, in the bigger scale, I know the scale could be, hundreds of square kilometers or thousands of square kilometers in the grid. So what we have to think about is a bigger scale, not a small pattern. A pattern scale cannot be that big. So we have to think in average, not particular which pattern, like the pattern formed by zooplankton. We have to make them in average. So that will be, we have to use, like if we have data, field data, satellite data, to do some data analysis to make the data comparable to our model data. So that is another issue I would think we should do for the zooplankton.
Thank you. Does the export campaign provide enough case studies of diel migration in the open ocean?
There is some, but I would like to see more of case study for the exports. So I see there's some quantitative study of to calculate how much of the export, um, but I would like to do more tests to see in the biggest scale that we are considering, um, annually how much carbon can be exported uh, by the zooplankton diel migration. Use the comparison with migration and without migration. So of course, without migration, we cannot tell in fact, we can only model with only can play with our model. That's so, but the comparison might be a good test to see the ecological impact from this movement. Uh, I think I would like to see more of that.
Can I ask a question about?
Sure.
So you were mentioning the whale pump earlier. Do we know how important the whale pump is for the contribution of the whale pump to the total carbon pump to the deep ocean, or even below the
Uh,
euphotic zone, let's say?
Yeah, there is a study I can share with you. This is the work done by Roman and McCarthy in, I think it published in 2010. I can show you. This is the work. Okay, can you see this? This is a pretty. I mean the whale pump study started in beginning of 20, before 2010, definitely. In 2004, 2003, there's some project supported this well pump study. And this paper is the result of that study.
Yeah.
Be interesting to look at it.
Yeah, I'll take a look. Yeah, I'm interested if
Do
they've
you
done
want me
it.
to do you want me to send you the link, or you can see it?
Uh, I wrote it down, but yeah,
Okay.
if you, yeah, thanks, thank you. I was
Okay.
just
Welcome.
curious because yeah, like
Magnitude.
if out of like the 30 to 50 to 30 to 60 petagrams of carbon per year exported below the euphotic zone, if the whale pump makes like even like a dent in that, or if it's but I guess they'll say in the paper. So I'll
Yes, I think the whale pump is playing some bigger role, particularly in the Southern Ocean.
yeah,
Um,
okay,
yeah, I think it's definitely worth taking a look. And um, I think maybe in the future, with more developing of the model, to add the whale factor would be a pretty good idea to see. Of course, the whale number is not, the individual animal is big, but
yeah,
the number is low.
yes, of course, yeah, yeah. That's why the question's so interesting.
Yes, it is
We'll find
very
out.
interesting, and also it's important.
Yeah, yeah.
Okay, the time is up. We have more questions, Xuemei. Paul and I would like to meet with you maybe at a later day this week, later time this week, and discuss more about this project. We want to thank you very much for your availability and coming to us to give us a talk about this very
Thank
interesting
you.
topic. We would like to know how to include such parameterization, such process in our model. Probably we will parameterize it. And yes, thank you very much for this.
Thank you. It's an honor to share with you guys our work. Thank you.
Us too.
Thank you.
Yes.
Thank you.
Thank you.
Thank you. Thank you.
Thank you. Bye.
Goodbye.
Bye.
Bye bye.